Hello friends, welcome back to another video. My name is Neo and I am Master Student of AI Study in Leuven, Belgium. In the previous video, we talked about the theory of the convolutional neural networks. So this video, we're gonna show you actually how to implement the first CNN architecture, which is the let 5 layers. So in the table is the details of each layer of this architecture. So we're gonna use the parameters in this table to design our network. So without further ado, let's get started. So let's first import the dataset that we are using. So we're gonna type from Keras dataset sets import minist. Okay. After that, we're gonna just start to load the data into both training set and test set. What we're gonna do here is to call this function from the minist. So minist load data, and here we want to split the data, load the data into both the training set and test set. Okay, so here we have the X train, Y train. So notice that X is the actual, we're gonna load the actual images data, and Y is actually the label of that images. So do the same for the test data, Y underscore test, and let's try to run this. And meanwhile, we're gonna import the matplotlib so that we can plot this plot those pictures to see what is going on. Plot as plt, and then let's first take a look at the shape of the training data. So notice that this X string is actually right now is a numpy array, so we can just use this shape. So if we load this, we are saying that it's 60,000 times 28 and 28. So it means that we actually have 60,000 training images, and with a size of 28 times 28 pixel. So let's take a look, just say one of them. So let's say single images, it's gonna be the X string and 0. So we're gonna pick the first images. So let's check the shape of these images, and it's 28 times 28. And let's use the plt im show single images, and let's plot it. So you see that it seems to be a shape of 5. So now we have an idea of the input images. Next, we're gonna actually pre-process the data. Notice that here actually the input image is actually 28 times 28. But if you remember from the architecture, actually the input should be 32 times 32. So we actually first need to pre-process the input images to increase it so that it can also be 32 times 22. 22. So actually we need to pre-process the images so that it can have the same input as a network. So what we're gonna here is actually import numpy as, and then we're gonna define a kind of like a function so that we will convert the 28 times 28 images into 32 times 32. So let's run this, and then let's check if it's working. So let's say in the beginning we have the X string shape, looks something like this. So it's 28 times 28. So let's try to run this function by saying X string equals path images times X string. So let's run it. It will take some time, but let's check again with the shape. So you see that now the X string is now having the pixel of 32 times 32. So let's do the same for the X test as well. So I'm just gonna copy this again, and then just test, just change it to test. Okay. Now let's also check what is the shape of X test. So now we have make sure that both the training images and the test images has the correct input for the network. Okay. So now this is actually the first step of the preprocessing. So now let's take a look at the label. So if you let's check the train. So it's basically an array, and it just contains the values of 5, then which is indicated what is actually the value of each images. And if you do the same for the test, yeah, it's basically the same. Here we need to actually apply a technique called one-hot encode so that the CNN can actually understand. Otherwise, it will actually think this as a kind of like sort of a regression problem. Inside of Keras, we have a very easy function to just do this. So we're going to call this from Keras and the utilities and numpy utilities and import to categorical. So if I say y train shape, now it's like 60,000, and then let's try to just convert to see what will happen if we do this. So we're gonna call this function called categorical, and then let's just pass in the y train, and let's see what is this y example is doing. So now it's actually kind of like the y label becomes kind of array. So let's check the shape of this. So you see that now the shape becomes 60,000 times 10. So actually one hot coding means that your actual label is gonna be the number that in this array is gonna indicate. For example, here in this example, if you have the 1 in the beginning, then it means that actually it indicates it's a label for 0. So now let's call this function for the training and the test label to category, and let's apply to the train. And if you input the parameter here as a 10, so it means that you want to actually encode this to a 10 category, so which in our case is that which is correct. So we're gonna name this as y category and train. Okay, so we will just copy this and do the same for the y test. So let's do this. Alright, so here we're actually gonna normalize the input images for the neural network. After normalization, we want the value of each pixel to be a value between 0 and 1. So in this case, we actually need to find the minimum and the maximum pixel value in the original pictures. So let's so remember that we already have an images object, and let's see what is the maximum of that one. So it's actually 255, which makes sense. So I suppose also for this is the minimum value should be 0. So for the normalization, we just need to divide all the data set with the maximum value here. So for example, x train is then equals to x train divided by the 255, and of course we're gonna do the same for the test. Let's see if it actually works. So let's use the scaled images, which is the x train now, and scaled images, what is the maximum of this? So you see that is a 1. But actually, if you just plot these images again using the PLT and show scale images, so it's actually pretty much the same if you printed it out compared to this. So notice that here, so if you check extreme shape, so it's the 60,000 stands for the number of the images. 32 times 32 is basically the width and the height of the images, but we are actually missing the channel. So in this case, because it's a grayscale images, so actually the channel number should be 1. So if it's RGB images, then it should be 3. So what are we gonna do here? It's quite straightforward. So we're gonna actually just use the reshape function, so that xstring equals to xstring reshape. And now, because we already know what kind of dimension we want, so this is 60,000, 32, 32, and 1. So let's run this, and then now let's check if the shape is done correctly. So now it's correct. Of course, we're gonna do the same for the training image data as well. So just change this to xtest and xtest. But remember that to change the number of the images. Now in this case, it's 10,000. So just make sure again check the input. So now they are correct. We have done the pre-processing for the input data. So now let's start to building and the training the model. To train the model, we actually to start to import some libraries for building the models. So we're gonna type from Keras models import sequential, and also we're gonna type Keras layers import dense convolutional 2D average pooling 2D, and then flatten. The first line we need to do is basically saying models equals to sequential. What you're gonna do to build this layer is actually just model add, and then you're gonna use the convolutional 2D, which is to define a convolution layer. So here you're gonna first put the parameters for the number of the filters. So here filters equals to 6, and we have kernel size equals to 5.5, and we need to choose also activation function. Activation, normally you should just choose the ReLU activation, and in the input size, which is the input shape of the images, and it will be 32, 32, and 1. Don't forget the 1 in the end. Okay, so we have built our first layer. So pooling layer, it's very easy because we're gonna just use the default setting, which is actually average pooling, and that's it. So here we're gonna just copy paste this. So in the second layer we have actually filter of 16 now. So let's just change this to 16, and the kernel size is still 5 times 5, and the stride is 1, which is the default, and you have the activation function. And here we actually don't have to specify this input shape anymore because it will actually automatically calculate it from the previous layer. So actually the input shape is only kind of like needed in this first layer. Before we come into the fully connected one, so we need to add a layer called the flatten. So what this layer do is actually just to convert this multiple feature map into a one long dimensional array. So here it's just flatten, and then this is what this layer is doing. For the first one, we're gonna just say model add, and we're gonna use this dense function here, and then units. So we're gonna say first output is 120, and we need to specify the activation function. So normally we just choose ReLU as the default one. So the second layer is again it's the same command, but now we need to reduce the units to 84. And this last one is the output layer. So for this one, we need to do something. So we need to change the units here as a 10. And also for the activation function, we're gonna switch from the ReLU to actually the soft commands. So what we're gonna do here, the last command is models compile, and then we have loss. We need to specify the loss function. Let's say this is use the categorical cross entropy, and let's say the optimizer. Let's optimizer using, let's say, the RMS prop, and the matrix we're gonna just use the accuracy. Here, let's call the model and the summary, so that you can see what is get the overview information of our build model. So let's just do this. Here you can actually check the output of after each layer. So, and you see that also the parameters for each layers. And if we check the output, that is actually completely matching what we initially specify here. So now let's start to training the model. Just needs to say model fit. So you're gonna put your training set data of the images, and then you just give them the category process the training label, and also you need to specify the approaches that you want to train, like how many iterations you want to run with your dataset. In this case, just for the demo process, let's just put the 2 on this. So let's just run this, and it will start the training. So after the training, the accuracy of the model is estimated to be 0.9804. So let's evaluate on the test set. So first we're gonna say models, and let's see what is the matrix name on this. So we're gonna use the loss and also the accuracy to evaluate this. So you just say model evaluate, and then you put the test dataset, and you also need to put the categorical label of the test set as well. So just run this. So the accuracy on the test set is actually 0.986. So if you want to see more details of the classification, you can use this schema matrix and import the classification report. Let's first get the predictions from the test set. So prediction equals models predict class, and let's put the X test set. So what you can do here, just to compare the actual classification report, you can just do this print and then classification report. Here you just put the Y test and prediction, and it will tells you for each class what is the precision on each one, and the recall rate and the F1 score and support. And here you see also the average accuracy from all the classes. So you think this network is quite actually good for classify those digit images. So that's all for building this network. So if you find this video useful, make sure to like and subscribe, and I will see you in the next one. Bye bye.